Imagine you are trying to cross a room. Just a normal room, maybe 10 meters wide. You start walking. To get to the other side, you first have to reach the halfway point, 5 meters. Fine. But to reach that halfway point, you first have to reach the halfway point of the halfway point, 2.5 meters. And to reach that, you need to reach 1.25 meters first. And before that, 62.5 centimeters. And before that, 31.25. Every step you take can be divided in half. And that half can be divided in half. And so on, forever. There is no smallest step. There is no first step. Before you can make any progress at all, you have to make half that progress first. Which means you have to complete an infinite number of steps just to cross a room. And yet, you do cross the room. You do it every day. You probably did it 10 minutes ago without thinking about it. That gap between what logic seems to prove and what obviously happens is a paradox. The word comes from the Greek para, meaning contrary to, and doxa, meaning opinion or expectation. A paradox is something that contradicts what you expected, something that shouldn't be true but seems to be, or that should be true but can't be. And tonight, we are going to explore every major paradox in mathematics and philosophy, slowly, one at a time, starting with the one you just walked through and ending with questions so deep that the greatest minds in history couldn't resolve them. Some of these paradoxes have answers, some don't. Some had answers that turned out to be wrong, and at least one proves that there are true statements in mathematics that can never, ever be proved. All of it, slowly, for sleep. For sleep, that rune-crossing paradox belongs to a Greek philosopher named Zeno of Elea, who lived roughly 2,500 years ago, around 490 before the Common Era. Zeno didn't propose his paradoxes because he was confused about walking. He knew perfectly well that people cross rooms and that fast runners overtake slow ones. His paradoxes weren't sincere expressions of doubt about the existence of motion. They were philosophical arguments, weapons, designed to support a specific philosophical position. He was trying to defend the philosophical position of his teacher, Parmenides, who argued that all change and motion are illusions. Reality, according to Parmenides, is one, unchanging and indivisible. Motion is something your senses tell you is happening. But your senses, according to Parmenides, are unreliable. Only reason reveals truth, and reason, as Zeno set out to demonstrate, shows that the concept of motion leads to contradictions. Aristotle took Zeno seriously enough to discuss his paradoxes at length, and he offered his own resolutions which modern mathematicians generally consider inadequate. The Stoics discussed them. Medieval Islamic and European philosophers discussed them. And when calculus was developed in the 17th century, mathematicians believed they had finally solved the paradoxes once and for all. Whether they actually did remains a matter of debate. He set out to show that the concept of motion leads to logical contradictions. If motion is real, Zeno argued, then absurdities follow, and if absurdities follow, then maybe motion isn't real after all. He produced several paradoxes, and at least 4 have survived. The one we started with is usually called the dichotomy, the paradox of cutting in half. Another is the Achilles paradox, which works like this. Imagine a race between Achilles, the fastest runner in Greece, and a tortoise. The tortoise gets a head start. By the time Achilles reaches the point where the tortoise started, the tortoise has moved a little further ahead. By the time Achilles reaches that new point, the tortoise has moved again. Each time Achilles catches up to where the tortoise was, the tortoise has inched forward. Achilles is closing the gap, but the gap never fully closes. Logically, he never catches the tortoise. Obviously, he catches the tortoise. Obviously, a fast runner overtakes a slow one. You can verify this by running a race against a slow animal. Achilles doesn't hover behind the tortoise forever, closing the gap by smaller and smaller fractions without ever crossing. He runs past. The paradox and reality disagree, and reality wins. But where exactly is the error in Zeno's reasoning? The steps are individually valid. The tortoise does move forward while Achilles catches up. The gap does shrink without reaching 0 in any individual step. Each step is shorter than the last. None of them is the finite step, because after every step there's another. Zeno has described an infinite process with no last step, and he's concluded from that the process never finishes. The modern answer involves infinite series, and it's worth walking through carefully because the resolution is as beautiful as the paradox is unsettling. When you add up an infinite number of terms that get smaller and smaller fast enough, the total can be finite. The series 1/2 plus 1/4 plus 1/8 plus 1/16, and so on forever, adds up to exactly 1. You can visualize this with a simple picture. Take a square with area 1, shade half of it, then shade half of the remaining unshaded area, then half of what's left, then half again. You're filling more and more of the square, approaching full coverage, never leaving a measurable gap. The total shaded area approaches 1, and in the limit, it equals 1. Not approximately 1, exactly 1. An infinite number of steps can be completed in a finite amount of time, because each step takes a proportionally shorter amount of time to complete. Zeno didn't know this. The mathematics of infinite series wouldn't be developed for another 2,000 years, and even then, the concept of adding infinitely many numbers and getting a finite result was controversial. Bishop Berkeley mocked the infinitesimals of calculus as ghosts of departed quantities. Some mathematicians argued that infinite sums were formal tricks without genuine mathematical meaning. Others argued they were essential tools that produced correct results and needed to be placed on firm ground. The debate lasted over a century before Augustin Louis Cauchy, Carl Weierstrass, and others developed the epsilon-delta formulation of limits that resolved the foundational questions and made infinite sums rigorous. Mathematicians in the 17th and 18th centuries argued bitterly about whether infinite sums were legitimate mathematical objects or dangerous nonsense. It took the rigorous development of calculus, particularly the concept of limits formalized in the 19th century, to put the answer on solid ground. But here is the thing. Even with the mathematics settled, Zeno's paradox still has teeth. The mathematical answer tells you that the infinite series converges. It tells you that the sum is finite. It doesn't tell you how you actually complete an infinite number of tasks in finite time. It answers the mathematical question while leaving the philosophical question untouched. And some philosophers argue that the philosophical question hasn't been fully answered to this day. Whether you find the mathematical resolution satisfying probably depends on what you think a paradox is. If a paradox is a logical puzzle with a definitive solution, then Zeno's paradoxes are solved. If a paradox is a situation where your intuition and your logic point in different directions, and the tension between them reveals something deep about the structure of reality, then Zeno's paradoxes are very much alive. There's a third paradox of Zeno's that's worth mentioning, the arrow. At any single instant, an arrow in flight occupies a specific position. At that instant, it isn't moving. It's just there, frozen, occupying a space exactly equal to its own length. But every moment in the arrow's flight is a single instant. If the arrow isn't moving at any single instant, and its flight is composed entirely of single instants, when does it move? This version attacks the concept of time itself. It asks whether time is made of instants the way a line is made of points, and if so, how continuous motion can emerge from a collection of motionless snapshots. Modern physics handles this with the concept of instantaneous velocity, the derivative, the limit of the change in position as the time interval shrinks to zero. The arrow does have a velocity at each instant, even though it doesn't change position during that instant. The velocity is encoded in the relationship between successive instants, not in any single one. But Zeno's arrow, like his dichotomy and his Achilles, lingers. The question of whether time is continuous or discrete, whether the universe ticks forward in smooth flow or in tiny quantized jumps, is still debated in theoretical physics. Zeno had a fourth paradox called the stadium, involving 3 rows of objects passing each other, which raises questions about the discreteness of space and time. If space and time are composed of smallest units, indivisible atoms of extent and duration, then an object moving past another object at twice the speed should skip over some of those units. But skipping a unit of space would mean the object was never in that location, which contradicts the assumption that it passed through every point between its start and end. The stadium paradox attacks discreteness the way the dichotomy attacks continuity. Together, Zeno's paradoxes form a pincer movement. If space and time are continuous, you need infinite series to cross a room. If space and time are discrete, objects skip locations as they move. Continuous or discrete, the concept of motion runs into trouble. Modern physics hasn't settled the question. General relativity treats spacetime as continuous. Quantum mechanics introduces discrete energy levels. Whether spacetime itself is ultimately continuous or discrete, whether there is a smallest length and a smallest duration, is an open question in theoretical physics, tied to the search for a quantum theory of gravity. Zeno was asking a question that physics hasn't fully answered 25 centuries later. Either way, they're 2,500 years old and people are still arguing about them. That is a remarkable shelf life for a philosophical argument. And while Zeno was attacking the concept of motion on the western coast of Greece, another philosopher in a different Greek city was attacking something even more fundamental. Not motion, not matter, not the physical world at all. He was attacking the concept of truth itself. The oldest and most dangerous paradox of self-reference was created by a philosopher from the Greek city of Miletus, around the 4th century before the Common Era, named Eubulides. His weapon was a single sentence. This statement is false. Read it again. If the statement is true, then what it says must be correct. And what it says is that it is false. So if it's true, it's false. But if it's false, then what it says is wrong. And what it claims is that it is false. If that's wrong, then the statement must be true. So if it's false, leads to true, leads to false, false leads to true, the sentence flips endlessly, like a coin that lands both sides at once. This is the liar's paradox, and for over 2,000 years it has resisted every attempt at resolution. It isn't a trick, it isn't a play on words. It is a genuine logical problem that reveals a crack in the foundations of language and logic. Aristotle discussed it. Medieval logicians spent centuries on it. In the 1930s, the Polish logician Alfred Tarski proved a theorem that turned the liar's paradox from a curiosity into a fundamental result. Tarski showed that any language powerful enough to talk about its own truth must either contain paradoxes like this one or be unable to define its own concept of truth. You can have a consistent language, or you can have a language that can talk about its own truth values. You can't have both. A language can define truth for a simpler language beneath it, an object language, but it can't define truth for itself without contradicting itself. Truth, in Tarski's framework, requires a hierarchy. Each level can discuss the truth of the level below, but no level can discuss its own truth without generating paradoxes. This result connects directly to Gödel's Incompleteness theorem, which was published 2 years earlier. Gödel showed that mathematical systems can't prove their own consistency. Tarski showed that languages can't define their own truthist. Both results are consequences of self-reference, and both reveal fundamental limits on what systems can say about themselves. That result is called Tarski's undefinability theorem, and it's one of the deepest results in mathematical logic. The liar's paradox also connects to something we'll encounter later tonight, a theorem that shook mathematics to its foundations. But that connection will make more sense after we've traveled a bit further. The paradox has variants that sharpen the dilemma. Consider 2 sentences. Sentence A says, sentence B is true. Sentence B says, sentence A is false. Neither sentence refers to itself directly, but together they create that oscillation. If A is true, then B is true, which means A is false. If A is false, then B is false, which means A is true. The self-reference is distributed across 2 sentences, making it harder to dismiss as a linguistic trick. Or consider the strengthened liar. This sentence is not true. If it's true, it's not true. If it's false, well, false means not true, so if it's not true, then what it says is correct, and it's true. The not true version blocks the escape route of saying the sentence is neither true nor false, because neither true nor false is a way of being not true. Logicians have spent careers on these variants, and the literature fills libraries. Every proposed solution, hierarchy of languages, pariconsistent logic, revision theory of truth, dialetheism, resolves some versions of the paradox while leaving others intact or generating new ones. The liar is, in a sense, the cockroach of logic. It survives every attempt to exterminate it. For now, note that this tiny sentence, 5 words long, has been defeating logicianing for 23 centuries. Let's move to something more concrete. What happens when you take a solid ball, cut it into pieces, and rearrange the pieces into two balls, each the size of the original. That sounds impossible. It sounds like a magic trick or a mistake, or the kind of claim that belongs in fiction rather than mathematics. You can't get something from nothing. You can't double the amount of matter in an object by cutting and rearranging. Conservation of mass is a fundamental principle of physics, and what Banach-Tarski describes seems to violate it outright. You can't create matter from nothing. You can't double the size of a ball just by rearranging its pieces. And yet, in 1924, two mathematicians working in Poland proved that you can. Stefan Banach was one of the founders of modern functional analysis and one of the most important mathematicians of the 20th century. Alfred Tarski was a logician whose work on truth and model theory would influence the foundations of mathematics for decades. Together, they published a result so counterintuitive that many mathematicians initially refused to believe it was correct. It was correct, mathematically. The result is now called the Banach-Tarski Paradox. Here is what it says, stated precisely. A solid ball in three-dimensional space can be divided into a finite number of pieces, and those pieces can be rotated and reassembled without stretching or bending into two solid balls, each identical in size to the original. Not approximately the size, exactly the size. Two balls from one, no gaps, no overlaps. No cheating. How? The answer lies in what pieces means. The pieces in the Banach-Tarski decomposition aren't normal shapes. They aren't cubes or slices or wedges. They are sets of points so wildly scattered, so infinitely complex that they have no meaningful volume. They aren't measurable. You couldn't weigh them or hold them or see them. They are so complex, so wildly scattered through the interior of the ball, that they have no meaningful boundary, no shape you could describe, no outline you could draw. They are clouds of points, intricately interlaced, defined by infinitely many choices made simultaneously through the axiom of choice. Nobody has ever drawn one. Nobody can. They exist only as abstract mathematical objects, defined by the axiom of choice, a foundational principle of set theory that allows you to make infinitely many selections simultaneously from infinitely many collections. The axiom of choice is itself controversial. Some mathematicians accept it because it's useful and consistent with the rest of mathematics. Others are uncomfortable with it because it produces results like Banach-Tarski, results that seem to violate physical reality. You might wonder how many pieces are needed. The answer, in the standard proof, is 5. Just 5 pieces, rearranged through rotations and translations, no stretching, no scaling, produce 2 complete balls from 1. 5. The number itself seems absurdly small for a result so extreme, but the pieces, again, aren't physical objects. They're abstract sets of points defined by the axiom of choice with no volume, no boundary, and no meaningful geometric shape. The paradox doesn't apply to physical objects because physical objects are made of atoms, and atoms have definite positions and can't be split into immeasurable sets. But the mathematical statement is true in the abstract world of pure mathematics. Volume isn't conserved under decomposition and rearrangement. Think about that for a second. Mathematics, the most precise language humans have ever developed for describing reality, contains a theorem that says you can double the volume of a ball for free. The theorem is correct, the proof is valid, and the result is insane. The Banach-Tarski paradox is sometimes cited as evidence that mathematics has gone off the rails, that the axiom of choice produces nonsense and should be abandoned. Most mathematicians disagree. The axiom of choice is necessary for many results that seem perfectly reasonable. It's needed to prove that every vector space has a basis, that every set can be well ordered, and that products of compact spaces are compact. Rejecting the axiom of choice to avoid Banach-Tarski would mean losing these results too, and most mathematicians consider that price too high. The deeper issue is what the paradox reveals about the relationship between mathematics and physical reality. We tend to assume that mathematical objects behave like physical objects, that volume should be conserved, that shapes should be measurable, that the rules of the physical world should apply to abstract spaces. Banach-Tarski shows that this assumption is wrong. Mathematical space is wilder than physical space. It contains objects that have no physical counterpart and obey no physical law. The paradox isn't a bug in mathematics. It's a feature of a system that is more general, more abstract, and less constrained than the physical world it was originally designed to describe. They treat it as evidence that our intuitions about volume and infinity are limited, not that the mathematics is broken. The paradox doesn't say that physics is wrong. It says that mathematical infinity behaves in ways that physical reality doesn't, and that the gap between the two is wider than anyone expected. Now let's visit a hotel. Not a normal hotel, a hotel with infinitely many rooms. The thought experiment that most clearly illustrates the strange behavior of infinity was proposed in lectures by one of the most influential mathematicians of the early 20th century, a German mathematician named David Hilbert, working at the University of Göttingen, which was at that time the world's leading center of mathematical research. Hilbert didn't just study infinity, he championed a program to formalize all of mathematics on rigorous logical foundations. The hotel paradox was his way of showing that infinity breaks the rules of arithmetic in ways that finite numbers never do. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, 4, and so on, with no last room. Every room is occupied. A new guest arrives and asks for a room. In a finite hotel, you'd have to turn them away. All rooms are full, but in Hilbert's hotel, you don't turn anyone away. You ask every guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. Every guest moves up one room. Since there's no last room, no guest is left without a room. And now room 1 is empty. The new guest checks in. An infinite hotel, completely full, just accommodated one more guest by shifting everyone over. Infinity plus 1 equals infinity. Now suppose a bus arrives with infinitely new guests. The hotel is full, and an infinite number of people need rooms. You ask every current guest to move to the room with double their current room number. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Every odd-numbered room is now empty. 1, 3, 5, 7, and so on. An infinite number of empty rooms. The infinitely many new guests fill those rooms. Infinity plus infinity equals infinity equals infinity. And now suppose infinitely many buses arrive, each carrying infinitely many passengers. An infinite number of infinitely large groups, all needing rooms. Hilbert's hotel can accommodate them all. The method involves a technique from number theory. You assign each bus a prime number and use powers of primes to encode which bus each passenger came from. Here is one method. Assign each bus a prime number. Bus 1 gets prime 2. Bus 2 gets prime 3. Bus 3 gets prime 5. Bus 4 gets prime 7, and so on. Each passenger on a bus is assigned a power of that bus's prime. Passenger 1 on bus 1 gets room 2 to the power 1, which is room 2. Passenger 2 on bus 1 gets room 2 to the power 2, which is room 4. Passenger 3 on bus 1 gets room 2 to the power 3, which is room 8. Passenger 1 on bus 2 gets room 3 to the power 1, which is room 3. Passenger 2 on bus 2 gets room 3 to the power 2, which is room 9. No two passengers from different buses will ever be assigned the same room, because different primes raised to different powers always produce different numbers. And there are infinitely many primes, so every bus gets its own encoding. Some rooms will be left empty, the room numbers that aren't powers of primes. That's fine. In an infinite hotel, wasting rooms doesn't matter. There are always more. The details are elegant, but the conclusion is what matters. Infinity times infinity still fits inside a single infinity. These aren't tricks or word games. They're consequences of the mathematical definition of infinity, formalized by Georg Cantor in the late 19th century. Cantor showed that a set is infinite if and only if it can be put into a one-to-one correspondence with a proper subset of itself. The set of natural numbers 1, 2, 3, 4 can be matched one-to-one with the set of even numbers 2, 4, 6, 8. Every natural number gets paired with exactly one even number, and vice versa. Both sets are equal in size, even though one is a subset of the other. That's what infinite means, a set that is equal in size to a part of itself. Cantor called this property countable infinity. A set is countably infinite if it can be put in one-to-one correspondence with the natural numbers. The even numbers are countably infinite. The integers, positive, negative, and 0 are countably infinite, even though they seem to contain twice as many numbers as the positive integers alone. The rational numbers, all fractions, are countably infinite, despite being densely packed on the number line, with infinitely many rationals between any two you can name. Each of these facts is a miniature Hilbert's hotel. The hotel of even numbers has room for the odd ones. The hotel of positive integers has room for the negatives. The hotel of rationals, despite having infinitely many guests between every pair of existing guests, is still only countably infinite. If that feels wrong, it should. Your intuition about size was built for finite collections, where a proper subset is always smaller than the whole. Infinite sets don't follow that rule. Hilbert's hotel is a thought experiment designed to make that failure of intuition vivid and memorable. It succeeds spectacularly. But there's a deeper point hiding inside the hotel. Infinity isn't just big. It's qualitatively different from any finite number, no matter how large. A hotel with 1 trillion rooms can fill up. A hotel with a Googleplex of rooms can fill up. Finite means there's a boundary, a limit, a point at which the resources are exhausted. Infinity means the resources are never exhausted. You can always shift everyone over. You can always make room. The difference between finite and infinite isn't a difference of degree. It's a difference of kind. This insight, that infinity is a different kind of thing, not just a very large number, was Cantor's great contribution to mathematics. Before Cantor, infinity was treated as a vague concept, a shorthand for as large as you like. After Cantor, infinity was a precise mathematical object with specific, surprising, rigorously provable properties. Hilbert's hotel is the simplest demonstration of those properties in action. Let the strangeness of that settle for a moment. If you're drifting, that's fine. Infinity doesn't need you to be awake. It was here before you were born, and it will be here long after. Hilbert's hotel has been running since Cantor opened it in the 1870s, and it has never turned away a guest. We've covered a paradox of motion, a paradox of truth, a paradox of volume, and a paradox of counting. Zeno said you can't cross a room. Eubulides said a sentence can be both true and false. Banach-Tarski said you can double a ball. Hilbert said a full hotel always has room. Each one reveals a place where human intuition collides with mathematical logic, and mathematical logic wins. What comes next is different. We're leaving the world of infinity and self-reference and entering the world of chance. The paradoxes ahead involve probability, situations where the correct answer feels so wrong that people refuse to believe it even after seeing the proof. The most famous of them involves 23 people and a birthday. How many people do you need in a room before there's a 50% chance that at least 2 of them share a birthday? Most people guess something around 180. After all, there are 365 days in a year, and you'd need to fill up roughly half of them before a collision becomes likely. Right? Wrong. The answer is 23. Put 23 randomly selected people in a room, and the probability that at least 2 of them share a birthday is about 50%. By the time you reach 50 people, the probability rises above 97%. At 70 people, it's virtually certain. This is the birthday paradox, and it isn't really a paradox in the logical sense. It doesn't involve a contradiction or an impossible conclusion. It's a case where the correct answer is so far from what intuition predicts that it feels wrong even after you've verified the math. The reason it works is that you're not asking whether any specific person shares a birthday with any other specific person. You're asking whether any pair in the group shares a birthday, and the number of possible pairs grows much faster than the number of people. With 23 people, there are 253 possible pairs. Each pair is an independent opportunity for a birthday match. Even though each individual pair is only a 1 in 365 chance of matching, 253 opportunities add up quickly. The birthday paradox is named a paradox not because the mathematics is contradictory, but because the answer violates nearly everyone's intuition. Most people anchor on the number of days in a year, 365, and reason that you need to fill up a significant fraction of those days before collisions become likely. They're thinking about the wrong comparison. They're comparing people to days. The birthday paradox is about comparing people to people, and the number of people-to-people comparisons grows much faster than the number of people. With 5 people, there are 10 possible pairs. With 10 people, 45. With 20 people, 190. With 23, 253. That combinatorial explosion is what drives the result. The formal calculation works by computing the probability that nobody shares a birthday, which is easier than computing the probability that someone does. The first person can have any birthday. The second person must avoid one day, probability 364 out of 365. The third person must avoid 2 days, 363 out of 365. And so on. By the 23rd person, you're multiplying together 22 fractions, each slightly less than 1, and the product drops below 1/2. The probability that nobody shares a birthday falls below 50%, which means the probability that someone does rises above 50%. It's elegant, it's counterintuitive, and it has practical applications in computer science, where birthday-style collisions appear in hash functions and cryptographic systems. The mathematics is straightforward. The surprise is entirely in the gap between what your gut tells you and what the numbers actually say. That gap between gut and math brings us to the most argued about probability puzzle in history. It has been debated in newspaper columns, academic journals, and dinner tables for decades. Thousands of people, including hundreds of professional mathematicians, have gotten it wrong, and many of them refuse to accept they were wrong even after being shown the proof. It involves 3 doors, a goat, and a game show host. The problem is named after Monty, the host of the American television show Let's Make a Deal, which ran from the 1960s through the 2000s. On the show, contestants chose between doors or curtains to win prizes. The mathematical version of the problem is a simplified abstraction of the game, stripped down to its essential structure. The setup is this. You are on a game show. There are 3 doors. Behind one door is a car. Behind each of the other 2 doors is a goat. You want the car. You pick a door. Let's say you pick door 1. Monty, the host, who knows what's behind every door, opens one of the doors you didn't pick and reveals a goat. He always opens a door with a goat. He never opens the door with the car. Let's say he opens door 3, and there's a goat behind it. Now there are 2 closed doors remaining. Door 1, which you picked originally, and door 2, which you didn't. Monty asks, do you want to switch your choice to door 2, or stay with door 1? Most people say it doesn't matter. There are 2 doors left. The car is equally likely to be behind either one. 50-50. Switching doesn't help. Most people are wrong. You should switch. Switching gives you a 2/3 chance of winning the car. Staying gives you 1/3. Here is why. When you initially picked door 1, there was a 1 in 3 chance the car was behind it. That hasn't changed. No new information about your door has been revealed. There was a 2 in 3 chance the car was behind one of the other 2 doors. When Monty opens door 3 and shows you a goat, he hasn't changed the total probability of the other 2 doors. He's concentrated that 2/3 probability onto the single remaining door. Door 2 now carries the full 2/3 probability that was previously split between doors 2 and 3. Another way to see it, if you picked the car initially, probability 1/3, switching loses. If you picked a goat initially, probability 2/3. Monty is forced to reveal the other goat, and switching wins the car. Switching wins 2/3 of the time because picking a goat initially happens 2/3 of the time. When the columnist Marilyn Vos Savant published the correct answer in Parade magazine in 1990, she received roughly 10,000 letters. The volume was extraordinary, but the tone was even more remarkable. Professors of mathematics wrote to tell her she was ignorant. Statisticians wrote to tell her she didn't understand probability. One professor wrote, "You blew it, and you blew it big." Another, "You are the goat." Another, from a university department, "Maybe women look at math problems differently than men." She was right. They were wrong. And the sheer ferocity of the disagreement reveals something important about this paradox. The incorrect answer just feels right. Well, this. It feels obviously right. It feels so obviously right that people become angry when told it's wrong. Psychologists have studied this reaction and found that it persists even after people are shown computer simulations demonstrating the 2/3 advantage. Something about the 3-door setup activates a cognitive bias called the equiprobability bias, the tendency to assume that if there are 2 remaining options, they must be equally likely. This bias is deep, automatic, and resistant to correction. It operates below the level of conscious reasoning. The Monty problem is not just a probability puzzle. It's a demonstration of the limits of human intuition in the face of conditional probability. And conditional probability, the way probabilities update when you receive new information, is the mathematical foundation of scientific reasoning, medical diagnosis, and artificial intelligence. Getting it wrong isn't just embarrassing in a game show context. Getting it wrong can have real consequences. The 50-50 intuition isn't a casual guess. It's a conviction. And it's a conviction that educated, mathematically sophisticated people hold with enough passion to write hostile letters to a stranger, many of them mathematicians and professors, telling her she was wrong. She wasn't. Computer simulations confirm it. Run the game 1,000,000 times and the switching strategy wins roughly 2/3 of the time, exactly as the mathematics predicts. You can write the simulation yourself in a few lines of code. The result is reproducible, unambiguous, and devastating to the 50-50 intuition. The mathematics confirms it, and yet the incorrect 50-50 intuition is so powerful that many people can't let go of it even after seeing the proof. The first time I genuinely accepted the Monty Hall solution, not as an abstract fact I'd been told, but as something I could feel was true, my entire relationship with probability changed. I stopped trusting my gut on anything involving chance. The gut is a pattern recognition system trained on everyday experience, and everyday experience doesn't prepare you for conditional probability. Here is another way to see it that many people find more convincing. Instead of 3 doors, imagine 100. You pick one. Monty opens 98 of the remaining 99 doors, all showing goats. One door remains closed. Would you switch? Almost everyone says yes. Your original door had a 1 in 100 chance. The remaining closed door carries the 99 in 100 chance that was spread across the other doors before Monty opened them. Switching is almost certainly right. The 3-door version works by exactly this logic. Your door had a 1 in 3 chance. The remaining door carries the 2 in 3 chance. The only difference is that 2/3 feels less compelling than 99 hundredths, even though the mathematical structure is identical. The gap between intuition and truth isn't a bug in human cognition. It's a feature of mathematics. The math is right. Your feelings about the math are noise. That insight, that mathematical truth is independent of how it feels, is going to become very important as we go deeper tonight. The paradoxes ahead are harder. Some of them have no correct answer. Some of them prove that correct answers can't exist. And some of them will ask you to accept conclusions so strange that the Monty Hall problem will seem pedestrian by comparison. If you're drifting off around now, that's fine. The probability paradoxes have a way of being genuinely tiring. They ask your brain to override its strongest instincts, and that takes energy. Let the mathematics rest for a moment. It'll still be there. The birthday paradox will still work with 23 people. The Monty Hall problem will still give you 2/3 if you switch, and your gut will still tell you both answers are wrong because your gut wasn't built for this. Human intuition about probability was shaped by a world where the relevant numbers are small, a few competitors for resources, a handful of threats to evaluate, a dozen members of a social group to keep track of. In that world, quick approximate reasoning works fine, but probability theory deals with large numbers, with combinatorial explosions, with combinatorial dependencies that cascade through layers of uncertainty. In that world, quick approximation fails, not occasionally, systematically and predictably. The birthday paradox and the Monty Hall problem aren't exotic edge cases. They're demonstrations that the tool evolution gave you for reasoning about chance is miscalibrated for the problems mathematics actually poses. Let us turn to a paradox that doesn't involve numbers at all. This one involves a question that sounds absurd, but turns out to undermine one of the most fundamental assumptions in logic. Can a set contain itself? Most sets don't contain themselves, psych. The set of all cats is not a cat. The set of all prime numbers is not a prime number. The set of all teaspoons is not a teaspoon. These sets are members of a much larger class, sets that do not contain themselves. Now consider the set of all sets that do not contain themselves. Call it R. Is R a member of itself? If R is a member of itself, then by definition it's a set that doesn't contain itself, because that's the rule for being in R. So if it's an ictats, if R is not a member of itself, then it satisfies the condition for membership in R. It's a set that doesn't contain itself. So if it's not in R, It is in, out, just like the liar's paradox. But this time, the consequences were devastating. This is Russell's paradox, discovered in 1901 by the British philosopher and mathematician Bertrand Russell. And it didn't just create a clever puzzle, it destroyed the entire logical foundation that mathematics was resting on. At the time, mathematicians were trying to build all of mathematics on a single foundation, set theory, developed primarily by Georg Cantor. The idea was that every mathematical object, numbers, functions, geometric shapes, everything, could be defined in terms of sets. Sets were supposed to be the bedrock, the atoms of mathematical reality, and the only rule for forming a set was the comprehension principle. Any well-defined property determines a set, namely the set of all objects that have that property. Russell showed that this principle leads to a contradiction. The property does not contain itself, is perfectly well defined, but the set it determines can't exist without contradicting itself. Gottlob Frege, who had spent years building a rigorous logical foundation for arithmetic based on the comprehension principle, received Russell's letter describing the paradox in 1902, just as the second volume of his life's work was being printed. Frege immediately recognized the devastation. He added an appendix acknowledging that the foundation of his system had collapsed. A scientist can hardly encounter anything more undesirable than to have the foundation give way just as the work is finished, he wrote. I was put in this position by a letter from Bertrand Russell. The honesty of that acknowledgement, written in a published appendix for all his colleagues to read, is remarkable. Frege didn't try to save his system or dismiss Russell's objection. He looked at the paradox, recognized that it was fatal, and said so. Few intellectuals in any field have responded to the destruction of their life's work with such grace. Russell himself was deeply affected by the paradox. He spent years trying to find a solution, and the effort contributed to his development of type theory and to the massive Principia Mathematica project with Whitehead. But the paradox also created in Russell a lasting suspicion of logical systems that claim to be complete or self-sufficient. He became, in a sense, permanently paradox-aware, always watching for the self-referential trap. The comprehension principle, the foundation of set theory, was broken. The response was a complete overhaul of the foundations of mathematics. Ernst Zermelo and Abraham Frenkel developed a new axiom system for set theory, now called Zermelo-Frenkel set theory, or ZERV, which restricts the kinds of sets you can form. You can't just define a set by any property. You have to build sets, step by step, from smaller sets, using specific approved operations. You start with the empty set. You can form pairs. You can take unions. You can take power sets. But you can't just define a set by stating a property and collecting everything that has it. That move, the move that seems so natural, so obviously correct, is exactly the move that creates the paradox. Russell and Alfred North Whitehead spent a decade writing Principia Mathematica, a massive 3-volume work that attempted to rebuild the foundations of mathematics without the comprehension principle, using a system of types that arrange mathematical objects into a strict hierarchy. Objects at level 0 are individuals, sets of individuals are at level 1, sets of sets are at level 2. No set can contain members from its own level or above, which prevents any set from containing itself and eliminates Russell's paradox. The system works, but it's cumbersome. Every familiar mathematical concept has to be defined separately at each level of the hierarchy, leading to enormous complexity. The work was monumental, nearly unreadable, and ultimately superseded by Zermelo-Frenkel's set theory, which achieved those goals more efficiently. But Principia Mathematica stands as one of the most ambitious intellectual projects in history, an attempt to make mathematics safe from its own paradoxes. The new system avoids Russell's paradox by making it impossible to form the troublesome set in the first place. But the deeper lesson of Russell's paradox isn't about any particular axiom system. It's about self-reference. Whenever a system is powerful enough to talk about itself, whenever a statement can refer to its own truth or a set can address its own membership, paradoxes lurk. The liar's paradox does it with sentences. Russell's paradox does it with sets. And as we'll see later tonight, Gödel's incompleteness theorem does it with proofs. Self-reference is the crack in every foundation, and it isn't confined to logic and mathematics. In computer science, the halting problem, proved unsolvable by Alan Turing in 1936, works by one mechanism. Turing showed that no computer program can reliably determine whether an arbitrary program will eventually stop or run forever. The proof uses self-reference. Assume such a program exists, feed it itself as input, and watch the contradiction unfold. The liar's paradox, Russell's paradox, Gödel's incompleteness, and Turing's halting problem are all, at their deepest level, a single phenomenon, self-reference creating irresolvable loops. From sets that contain themselves, let us drift to a question about identity. This one is older than mathematics, older than logic, older, possibly, than philosophy itself. If you replace every plank of a wooden ship, one at a time, until every piece of wood is new, is it still that ship? This is the ship of Theseus, and it has been discussed since at least the 1st century, when the Greek writer Plutarch described it. Theseus, the mythical king of Athens, had a ship that was preserved in the harbour as a memorial. Over the years, the wooden planks rotted and were replaced. Eventually, every plank had been replaced. Plutarch asked, "Is the restored ship of Theseus?" The puzzle sat for over 1,000 years, discussed by philosophers from Heraclitus to the medieval scholastics, before the English philosopher Thomas Hobbes added a twist that made it genuinely insoluble. Suppose someone collected all the old planks as they were removed and built a second ship from them. Now you have two ships. One is made of the new planks, sitting in the harbour where the original sat. The other is made of all the original planks, assembled in the original configuration. Which one is the ship of Theseus? This isn't a mathematical paradox in the formal sense. There's no logical contradiction, no impossible conclusion, no proof that something can't exist. It's a paradox of identity, a case where our concept of sameness doesn't give a clear answer. We feel strongly that objects persist through time, that your car is still your car after you replace the tires, that you are still you after every cell in your body has been replaced. But when we try to make that feeling precise, it falls apart. The paradox has no universally accepted resolution. Different philosophical traditions give different answers. Some say identity is tied to continuity. The ship is still the ship of Theseus as long as the replacement is gradual. Others say identity is tied to material composition. The ship made of the original planks is the real one. Others say identity is a human convention rather than an objective fact, and the question has no right answer because there's nothing in the universe that determines which ship is really the ship of Theseus. In ancient China, the philosopher Gongsun Long posed a related puzzle around the 3rd century before the Common Era. He argued, in a famous dialogue, that a white horse is not a horse. The argument runs roughly as follows. If you ask for a horse, any horse will satisfy the request. Bay, black, white. If you ask for a white horse, only a white one will do. Since horse is satisfied by things that don't satisfy white horse, the two concepts have different extensions. They refer to different collections of objects. Therefore, Gongsun Long argued, a white horse is not a horse. The concept white horse is distinct from the concept horse. The conclusion sounds absurd. Obviously, white horses are horses. But the argument exposes a genuine tension in how categories work. Is a category defined by what it includes or by what it means? Horse includes all horses regardless of color. White horse includes only white ones. They include different things, which means they're different categories. Gongsun Long wasn't confused about horses. He was probing the relationship between properties and categories. His reasoning was that horse refers to a shape, while white horse refers to a shape and a color. And since shape plus color is a different concept from shape alone, a white horse is not a horse. The argument sounds absurd, but it raises genuine questions about the relationship between categories, properties, and identity, questions that would eventually become central to mathematical logic and set theory. The ship of Theseus and the white horse paradox both point to a gap in our concepts that mathematics alone can't fill. Some questions aren't answered by calculation. They're answered, if at all, by deciding what your words mean and accepting the consequences. The paradox isn't ancient. It's alive in every modern debate about personal identity, about the preservation of historical artifacts, about what it means for a software program to be the same program after extensive updates. When a company replaces every employee over a decade, is it still that company? When a city rebuilds every building, is it still that city? When the cells in your body are replaced on roughly a 7-year cycle, are you still the person you were a decade ago? Neuroscience adds another layer. Your brain's neural connections change continuously. Memories are reconstructed every time you recall them, slightly altered each time. The person who remembers your 10th birthday isn't the physical entity that experienced it. Different atoms, different cells, different neural pathways. If identity requires physical continuity, you aren't who you were a year ago, let alone a decade. Most people reject that conclusion. We feel, powerfully and continuously, that we are the same person over time. That feeling of persistent identity is one of the most fundamental features of human consciousness. The ship of Theseus asks whether that feeling corresponds to anything real, or whether it's a useful illusion that evolution installed because organisms that believe they persist over time make better plans than organisms that don't. These questions don't have mathematical answers. They have philosophical answers, and the answers depend on what you mean by same. The ship of Theseus is the paradox that forces you to decide what you mean, and sometimes the consequences are uncomfortable. Let us move to a paradox that combines logic, probability, and dread in roughly equal measure. A judge tells a prisoner, "You will be hanged on one day next week, but you won't know which day until the morning of the execution. The hanging will be a surprise." The prisoner reasons as follows. The hanging can't be on Friday, because if he's still alive on Thursday evening, he'll know Friday is the last possible day, and the hanging won't be a surprise. So Friday is eliminated. But if Friday is eliminated, then the hanging can't be on Thursday either. If he's still alive on Wednesday evening and Friday is already ruled out, he'll know Thursday is the last possible day, not a surprise. Thursday is eliminated. By the same reasoning, Wednesday, Tuesday, and Monday are all eliminated. The prisoner concludes that the hanging can't happen at all because there's no day on which it could be a surprise. On Wednesday morning, the executioner arrives. The prisoner is surprised. This is the unexpected hanging paradox, also called the surprise examination paradox. In the exam version, a teacher tells students there will be a surprise quiz next week, but they won't know which day until the quiz arrives. Students reason their way to the conclusion that the quiz can't happen on any day, are shocked when it happens on Wednesday, and realize their reasoning failed even though each step seemed valid. The exam version makes the paradox more accessible, but doesn't resolve it. The core question remains. How can a prediction about surprise be self-defeating in reasoning but self-fulfilling in practice? The prediction says, "You'll be surprised." Your attempt to use the prediction to avoid surprise fails, and you are surprised, exactly as predicted. The prediction was correct precisely because your attempt to incorporate it into your reasoning undermined itself. This is the unexpected hanging paradox when framed as a surprise test. The prisoner's reasoning seems airtight at each step, but the conclusion, that the hanging can't happen, is obviously wrong. The hanging does happen, and the prisoner is surprised, exactly as the judge said. What goes wrong in the prisoner's reasoning? This is genuinely debated. Some logicians argue that the prisoner's error is in the backward induction, that eliminating Friday is valid, but the subsequent elimination of Thursday relies on the prisoner knowing that he knows Friday is eliminated, which is a different and more questionable claim. Others argue that the statement "the hanging will be a surprise" is self-referential in a way that makes it immune to the kind of logical analysis the prisoner applies. Others argue that the paradox reveals a genuine inconsistency in the concept of knowledge about future events. One particularly sharp analysis comes from the mathematician Timothy Chow. He argues that the prisoner's error is in assuming he can use the judge's statement as a premise in his reasoning. The judge said, "The hanging will be a surprise." If the prisoner uses this as a logical axiom, he can derive that the hanging can't happen. But the judge didn't say you can logically prove that the hanging will be a surprise. The judge made a factual prediction about the prisoner's psychological state. The prisoner treated a prediction about his own knowledge as a logical constraint on reality. Those are different things, and conflating them is where the reasoning goes wrong. But this analysis is itself debatable. If the judge is known to be perfectly reliable, if every prediction the judge has ever made has come true, then the prisoner seems justified in taking the statement as a logical premise, and the paradox regenerates. There is no consensus. The unexpected hanging paradox sits in the uncomfortable space between logic and epistemology, and it has been there since at least the 1940s, when it first appeared in print. Like the liar's paradox, it involves self-reference. Like the Monty problem, it involves conditional reasoning that defies intuition. But where the Monty problem has a definitive correct answer, the unexpected hanging does not. It sits in a category by itself, a paradox where the reasoning is valid at each step. The conclusion is clearly false, and nobody can agree on which step is the error. Some logicians have suggested that the paradox is a genuine paradox of knowledge, that the concept of surprise is inherently self-undermining when applied to a situation the subject can reason about. If you know that an event is supposed to surprise you, that knowledge prevents the surprise, which means the prediction was wrong, which means you have no basis for ruling out any day, which means the event can surprise you after all. The reasoning cycles endlessly, and the cycling is the point. There may be no stable answer. And like the ship of Theseus, it may not have a definitive answer. If you're still here, we're about halfway through. What comes next are the paradoxes that changed mathematics itself, the ones that forced mathematicians to redraw the boundaries of what can be known and what can be proved. And the first one involves a question that sounds innocent. Are some infinities bigger than others? The mathematician who proved that infinity comes in different sizes and whose proof is so simple that you can follow it lying in bed with your eyes closed was a German mathematician named Georg Cantor, working in the 1870s and 1880s at the University of Halle. Cantor didn't just contribute to mathematics, he created an entirely new branch of it, the theory of infinite sets, and the result he's most famous for, the diagonal argument, is one of the most elegant proofs in the history of human thought. Start with a question. Are there more counting numbers, 1, 2, 3, 4, 5 and so on forever, or more real numbers between 0 and 1? Your first instinct might be that the counting numbers win because they go on forever. But the real numbers between 0 and 1 also go on forever. 0.1, 0.01, 0.001. There are infinitely many of them. Both sets are infinite. Are they one infinity? Cantor showed they aren't. The real numbers between 0 and 1 constitute a strictly larger infinity than the counting numbers. Here is the proof. Suppose, for the sake of argument, that you could list every real number between 0 and 1. A complete list, numbered 1, 2, 3, 4, and so on, with every real number between 0 and 1 appearing somewhere on the list. Cantor showed that this assumption leads to a contradiction. Take your supposed complete list. Look at the first digit after the decimal point of the first number. Look at the second digit of the second number, the third digit of the third number, the fourth digit of the fourth number. You're reading digits along the diagonal of your list. Now construct a new number. This is the key move, and it's worth following carefully because once you see it, the proof becomes undeniable. Look at your list. Suppose the first number on your list is 0.51739. The second number is 0.42805. The third is 0.88142. The fourth is 0.39671. Read the diagonal. The first digit of the first number is 5. The second digit of the second number is 2. The third digit of the third number is 1. The fourth digit of the fourth number is 7. Now change each diagonal digit. 5 becomes 6. 2 becomes 3, 1 becomes 2, 7 becomes 8. Your new number starts 0.6328 and continues with every digit chosen to differ from the corresponding diagonal digit. This new number can't be the first number on your list because it differs from the first number in the first decimal place. It can't be the second because it differs in the second decimal place. It can't be the third, fourth, hundredths, or millionth number because at each position the digit was deliberately chosen to be different. It can't be anywhere on the list. For each diagonal digit, choose a different digit. If the diagonal digit is 7, write 3. If it's 4, write 8. Anything, as long as it's different from the diagonal digit at that position. The number you've constructed differs from the first number on the list in its first digit, from the second number in its second digit, from the third number in its third digit, and so on for every number on the list. Your new number is different from every number on the list. It can't be anywhere on the list, because wherever it might be, it differs in at least one digit. But you assumed the list was complete. Every real number between 0 and 1 was on it. And now you found a real number that isn't on it. Contradiction. The original assumption was wrong. You can't list all the real numbers between 0 and 1. There are more real numbers than counting numbers. The infinity of real numbers is strictly larger than the infinity of counting numbers. Let that proof settle for a moment. It's short, it's elementary, no advanced mathematics required, just counting and diagonal reading, and it proves something that seems impossible. There are more numbers between 0 and 1 than there are counting numbers. The infinity of the continuum is strictly larger than the infinity of whole numbers, and the proof is so clean that once you've seen it, you can't unsee it. The new number is right there, constructed digit by digit, provably absent from any list you could ever write. Cantor went further. He asked whether there's an infinity between the counting numbers and the real numbers, a set bigger than Aleph EFEFTFDFDS, null but smaller than the continuum. He conjectured that there isn't, that the continuum is the next infinity up from the countable one. This conjecture, called the continuum hypothesis, turned out to be independent of the standard axioms of set theory. It can't be proved or disproved. It is neither true nor false within the system. It's a statement that the axioms don't determine, a mathematical free variable. Gödel proved in 1938 that it can't be disproved. Paul Cohen proved in 1963 that it can't be proved. Together, these results showed that one of the most natural questions about infinity has no answer within the standard framework of mathematics. Cantor called the infinity of the counting numbers Aleph null, the smallest infinite cardinal number. The infinity of the real numbers is larger, and Cantor showed that for any infinite set, you can always construct a larger infinity by taking the set of all subsets of the original set. There is no largest infinity. Infinities grow without bound, each one dwarfing the one before it, an infinite tower of infinities ascending without end. The idea was not entirely without precedent. In India, Jain mathematicians had contemplated different sizes of infinity as early as the 4th century before the Common Era, classifying infinities into categories and recognizing that some were larger than others. They didn't have Cantor's formal framework, but the intuition that infinity isn't a single undifferentiated concept was present in their philosophical tradition centuries before European mathematics addressed the question. Cantor spent the last 3 decades of his life defending his work against critics who considered it meaningless, dangerous, or both. He gave up working on set theory for extended periods, turning instead to literary criticism and to a quixotic attempt to prove that Francis Bacon wrote Shakespeare's plays. His mathematical isolation deepened as the attacks continued. His contemporaries were less receptive than history would suggest. Leopold Kronecker, one of the most powerful mathematicians in Germany, called Cantor a scientific charlatan and a corrupter of youth. Henri Poincaré called his work a disease. Cantor suffered severe bouts of depression throughout his career, spent time in psychiatric institutions, and died in a sanatorium in 1918. Like Boltzmann, like Bashevsky, like so many others, he was right, and his contemporaries were wrong, and the recognition came too late to help. Cantor's mental health deteriorated in the 1890s. He was hospitalized repeatedly for what may have been bipolar disorder, though diagnosis at this historical distance is unreliable. During periods of relative health, he worked on mathematics, on the continuum hypothesis, and on his ultimately futile Bacon-Shakespeare project. During episodes of depression, he was unable to work at all. His professional isolation deepened as Kronecker continued to block his career advancement and discourage journals from publishing his work. He died on January 6, 1918, in a sanatorium in Halle alone. He was 72. Within a decade of his death, his theory of infinite sets had become the standard foundation for all of mathematics, taught in every university, used in every branch of the subject. The man who was called a charlatan by his contemporaries is now considered one of the greatest mathematicians who ever lived. The tragedy of Cantor's life mirrors patterns we've seen before. Boltzmann, Lobachevsky, Galileo, so many others who were right too early and paid for it with their peace of mind or their lives. The gap between discovery and recognition in mathematics, as in every science, is often measured in decades, sometimes in lifetimes. Today, Cantor's theory of infinite sets is the foundation of modern mathematics. The diagonal argument is taught in every undergraduate mathematics program in the world, and the idea that some infinities are bigger than others, an idea that seemed insane to Cantor's critics, is now as settled and uncontroversial as the idea that the Earth orbits the Sun. And now we arrive at the paradox that shook mathematics harder than any other, the one that proved there are limits to what logic can achieve, the one that showed that any sufficiently powerful mathematical system must contain truths it cannot prove. In 1931, a 25-year-old Austrian logician published a paper that ended the dream of a complete and consistent foundation for mathematics. His name was Gödel, and the paper contained his two incompleteness theorems, results so profound that the mathematical community is still absorbing their implications nearly a century later. To understand what Gödel proved, you need to understand what he was responding to. In the early 20th century, the most ambitious project in mathematics was David Hilbert's program. Hilbert's program was the culmination of a century-long effort to make mathematics rigorous. In the 1800s, mathematicians had discovered paradoxes and inconsistencies in calculus, in geometry, and in the theory of infinite sets. Each time they had responded by tightening the foundations, formalizing definitions, strengthening axioms, eliminating vague concepts. Hilbert wanted to finish the job. He wanted to formalize all of mathematics into a single axiomatic system and then prove that the system was both consistent, free of contradictions, and complete, capable of proving or disproving every mathematical statement. If Hilbert's program succeeded, mathematics would be settled, every question would have an answer, and the system would contain the machinery to find it. Gödel demolished this dream. His first incompleteness theorem says, any consistent formal system that is powerful enough to describe basic arithmetic contains statements that are true but unprovable within the system, not just hard to prove, not just currently unproven, fundamentally, inherently, necessarily unprovable, true, but beyond the reach of proof. His second incompleteness theorem says, any consistent formal system powerful enough to describe basic arithmetic cannot prove its own consistency. The system can't verify that it's free of contradictions using only its own rules. If it could, it would be inconsistent. The method Gödel used is itself a kind of paradox. He constructed a mathematical statement that essentially says, this statement is not provable. If the statement is provable, then it's true, which means it's not provable. Contradiction. So it can't be provable. But if it can't be provable, then what it says is correct. It really isn't provable. So it's true, a true statement that the system can't prove. Gödel's method is ingenious. He assigned a unique number to every symbol, every formula, and every proof in the system. A technique now called Gödel numbering. The idea is to encode the structure of mathematics within mathematics itself. Every symbol gets a number. The plus sign might be number 1. The equal sign might be number 2. The numeral 0 might be number 3. A formula is a sequence of symbols, so it can be encoded as a sequence of numbers. A proof is a sequence of formulas, so it can be encoded as a sequence of sequences of numbers. With the right encoding, every mathematical statement about proofs becomes a mathematical statement about numbers. This numbering, now called Gödel numbering, translates statements about mathematics into statements about numbers. A statement like this sequence of symbols constitutes a valid proof becomes a statement about whether a certain number has a certain arithmetic property. With this translation in place, Gödel could construct a sentence that says, in effect, the number corresponding to this sentence has the property of being unprovable. The sentence talks about numbers, the numbers encode sentences, the sentence talks about itself, through the intermediary of arithmetic. The construction is breathtaking in its elegance. Gödel didn't just find a true but unprovable statement. He built a machine for generating them. Any consistent system powerful enough to do arithmetic contains such statements. You can add the unprovable statement as a new axiom, but the expanded system immediately generates new unprovable statements of its own. The incompleteness is not a local flaw, it's a structural feature of formal systems of sufficient power. The connection to the liar's paradox is deliberate. Gödel took the self-referential structure of "this statement is false" and translated it into the language of formal mathematics. The liar's paradox creates a sentence that can't be true or false. Gödel's sentence creates a statement that is true but can't be proved. Self-reference, again, is the crack in the foundation. The implications are staggering. There is no complete axiom system for mathematics. No matter how many axioms you add, no matter how carefully you construct your system, there will always be true statements that escape proof. Mathematics is inexhaustible, not because mathematicians are slow, but because truth outpaces provability in any system complex enough to talk about numbers. When I first understood what Gödel's theorem actually says, not as a vague claim about limits of knowledge, but as a precise mathematical result with a specific proof, something changed in how I thought about certainty. Before Gödel, I assumed that if something was true, it could, in principle, be proved. That truth and provability were the same thing. After Gödel, I knew they weren't. Truth is bigger than proof, and that gap between truth and proof will never close. Gödel's theorem didn't just end Hilbert's program. It changed the philosophical landscape of mathematics permanently. Before Gödel, many mathematicians and philosophers held a view called formalism, the idea that mathematics is essentially a game played with symbols according to rules, and that the meaning of mathematical statements is exhausted by their formal properties. Gödel's theorem showed that formalism can't be the whole story. There are truths that the formal system can't capture, which means either mathematical truth extends beyond any formal system, or the concept of mathematical truth itself needs to be revised. The logician and philosopher Willard van Orman Quine called Gödel's incompleteness theorem the most significant mathematical result of the 20th century. The mathematician John von Neumann, who was in the audience when Gödel first presented his result at a conference in Königsberg in 1930, immediately grasped its significance and reportedly abandoned his own work on the foundations of mathematics, saying that Gödel had settled the question in the negative. Hilbert reportedly was not happy about Gödel's result. The dream of a complete, consistent, decidable foundation for all of mathematics, the dream Hilbert had spent decades pursuing, was shown to be impossible, not difficult, not impractical, logically impossible. Gödel himself had a complicated life. He became close friends with Albert Einstein at the Institute for Advanced Study in Princeton. The two of them walked together almost daily, an odd pair. Einstein gregarious and warm, Gödel reserved and anxious. Einstein reportedly said that in his later years, his own work no longer mattered much to him, and that he came to the Institute mainly for the privilege of walking home with Gödel. Gödel, for his part, proved a result in general relativity, showing that Einstein's equations allow for universes in which time travel is possible, a finding that delighted Einstein and disturbed everyone else. He suffered from paranoia throughout his life and eventually became convinced that people were trying to poison him. He refused to eat unless his wife Adele tasted his food first. When Adele was hospitalized for an extended period and couldn't taste his food, Gödel stopped eating. He died in 1978 of self-starvation, weighing roughly 30 kilograms. He was 71 years old. The man who proved that truth exceeds proof died of a paradox of his own. The fear that killed him was irrational, but the system he used to evaluate risk, his own mind, couldn't prove to him that it was safe to eat. If you're drifting off, that is fine. Gödel's theorem will still be true tomorrow. It will be true in every axiom system anyone will ever construct. It is one of the very few results in mathematics that can never be superseded because it's a statement about the limits of proof itself, and those limits don't change with the addition of new axioms or new techniques. Every future mathematics, no matter how advanced, will contain truths it cannot prove. That fact is as permanent as anything in human knowledge. Let that sit for a moment. We've moved from paradoxes of motion and truth to paradoxes that reshape the boundaries of mathematics itself. Zeno's paradoxes were resolved by calculus. The liar's paradox was absorbed into theories of truth. Russell's paradox was resolved by rebuilding the foundations of set theory. But Gödel's incompleteness isn't a problem to be fixed. It's a fact about the nature of mathematical truth. It doesn't go away. It applies to every system, forever. Let's come back to Earth. We've spent a long time in the stratosphere of abstract logic. and the air is thin up there. The next few paradoxes are closer to everyday experience. They involve money, measurement, and decisions. The next paradox involves money, gambling, and a game that's worth infinite money, but that nobody in their right mind would pay $20 to play. Imagine a coin-flipping game. You flip a fair coin. If it comes up heads on the first flip, you win $2. If the first flip is tails and the second is heads, you win $4. If the first two are tails and the third is heads, you win $8. Each additional tails flip before the first heads doubles the prize. Tails, 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 heads. $16. Tails, tails, heads. $32. Tails, tails, tails. $32. And so on. How much should you pay to play this game? The infinite main time is there. The probability of winning $2 is 1/2. The probability of winning $4 is 1/4. The probability of winning $8 is 1/8. And here's the key pattern. 2 times 1/2 is 1. 4 times 1/4 is 1. 8 times 1/8 is 1. 16 times 1/16 is 1. Each outcome contributes $1 to the expected value. 2 times 1/2 is 1. 4 times 1/4 is 1. 8 times 1/8 is 1. Each term in the sum is 1, and there are infinitely many terms. The expected value is 1 plus 1 plus 1 plus 1 forever. Infinity. If the expected value is infinite, you should be willing to pay any finite amount to play. $1,000, a million, a billion. The expected return exceeds any price. But would you pay even $20? Probably not. Most people wouldn't pay more than about 10. The game almost always pays out very little. 50% of the time you win just $2, 75% of the time you win $4 or less, and the astronomical payoffs that drive the expected value to infinity are vanishingly unlikely. This is the St. Petersburg Paradox, named after the Journal of the St. Petersburg Academy of Sciences, where it was first published by Daniel Bernoulli in 1738. The paradox was actually posed by Bernoulli's cousin Nicolaus, and Daniel's resolution using utility theory was one of the founding contributions to what would eventually become modern economics. Before Bernoulli, economists and gamblers implicitly assumed that the value of money was proportional to the amount, that $200 was exactly twice as good as $100. Bernoulli argued that this is psychologically false. The jump from $0 to $100 changes your life more than the jump from $1 million to $1 million and $100. Value is subjective and diminishing. It reveals a disconnect between expected value, which is the mathematical measure of what a game is worth, and the actual value a rational person would assign to it. Bernoulli's resolution was to introduce the concept of utility, the idea that the value of money isn't proportional to the amount. Your first $1,000 is worth more to you than your millionth $1,000. The utility of money is logarithmic. Each doubling of your wealth adds a roughly constant amount of happiness. When you calculate the expected utility of the St. Petersburg game instead of the expected value, you get a finite number, and a modest one at that. But even Bernoulli's solution isn't fully satisfying. You can modify the game to restore the infinite expected utility by increasing the payoffs faster. The paradox keeps regenerating. Like a mathematical hydra, cut off one head and two grow back. Modern economists and decision theorists continue to debate it. Some argue that infinite expected values are simply not meaningful for finite beings with finite lifespans. Others argue that the paradox reveals a genuine limitation in expected value theory as a guide to rational decision-making. There is a deeper lesson here about the limits of expected value as a guide to decision-making. Expected value assumes that you care about the average outcome over infinitely many repetitions. But you don't play infinitely many times. You play once. And in a one-shot game, the expected value can be arbitrarily misleading. A game that pays $1 billion with probability 1 in a billion and 0 otherwise has an expected value of $1, equivalent to a game that definitely pays $1. But no rational person would treat these two games as equivalent. Thus equivalent these two games. Petersburg Paradox pushes this to its extreme. A game whose expected value is infinite but whose median payout is $2 If you judge by the expected value, the game is worth everything. If you judge by what's likely to actually happen, it's barely worth anything. The paradox forces you to choose between two ways of measuring value, and neither choice is fully satisfying. Either way, it's a game worth infinite money that you wouldn't play for the price of lunch. And that tells you something important about the gap between mathematical models and human reality. From a paradox about money, let's move to a paradox about measurement that connects directly to something we explored in the geometry script. How long is the coast of Britain? The answer, as the mathematician Benoit Mandelbrot showed in 1967, is, it depends on how closely you look. Mandelbrot was a Polish-born, French-raised mathematician working at IBM's Thomas J. Watson Research Center, an unusual position for a mathematician, and one that gave him access to computing resources most academics lacked. He thought visually in an era when mathematics was dominated by algebraic abstraction. He was interested in roughness, in the jagged and irregular shapes that Euclidean geometry had nothing useful to say about. The coastline question was his way of demonstrating that the concept of length itself breaks down when applied to natural shapes. Measure the coastline with a ruler 100 kilometers long, and you get one number. Measure with a 10-kilometer ruler, following the bays and inlets more closely, and you get a larger number. 1-kilometer ruler. Larger still. 1 meter, and the coastline grows enormously. 1 centimeter, and you're tracing around individual rocks. The shorter the ruler, the longer the coast, and there is no natural stopping point. As the ruler shrinks towards zero, the measured length grows without bound. And the coastline of Britain is infinitely long. This is the coastline paradox, and it isn't a trick. It's a genuine property of coastlines and many other natural shapes. The roughness goes all the way down. At every scale, there are more wrinkles, more irregularities, more detail that a shorter ruler would catch. Mandelbrot identified a numerical property of these shapes that captures their roughness, fractal dimension. A smooth line has dimension 1. A flat surface has dimension 2. But a jagged coastline fills more space than a line without filling a full surface. Its dimension is somewhere in between, a fraction. The coast of Britain has a fractal dimension of roughly 1.25, more than a line, less than a surface. A dimension that isn't a whole number, defying a concept that everyone assumed could only take integer values. Mandelbrot called shapes like this fractals and showed that they're not mathematical curiosities. They describe the actual geometry of nature. Trees branch into smaller branches into smaller branches. Lungs divide into smaller and smaller tubes. River networks fork into tributaries into streams. None of these shapes are smooth at any scale. The paradox reveals something unsettling about measurement itself. The length of a coastline isn't a fixed number. It's a function of the resolution you use. There is no true length, only lengths at various scales. The coastline paradox has implications beyond geography. It applies to any measurement of a rough or irregular boundary. The surface area of your lungs, the length of a river, the boundary of a cloud, the edge of a forest. All of these are fractal-like, with detail at every scale, and all of them get larger as you measure more precisely. The true measurement depends on the resolution, and there's no natural resolution to choose. This challenges a deep assumption of classical physics that objects have definite, well-defined geometric properties. A sphere has a definite surface area. A cube has a definite edge length. But a coastline doesn't have a definite length, and a cloud doesn't have a definite surface area. These objects exist in the physical world. You can see them and touch them, but their geometric properties are resolution-dependent, which means that the seemingly simple question, "How long is this?" doesn't always have a simple answer, even for objects you can walk along and touch. A coastline is as real and as tangible as any geometric shape. You can stand on it, you can photograph it, but it doesn't have a length, not in the way a ruler or a highway has a length. Its length is infinite, or more precisely, its length depends on the scale at which you choose to measure it. The concept of length, which seems so simple and so fundamental, breaks down when applied to fractal shapes. And fractal shapes, as Mandelbrot showed, are what nature actually produces. The smooth shapes of Euclidean geometry are the exception. The rough shapes of fractal geometry are the rule. Let's move to a paradox that divides decision theorists into two warring camps. neither of which has been able to defeat the other in over 50 years of argument. A superintelligent being, call it the predictor, presents you with two boxes. Box A is transparent and contains $1,000. Box B is opaque. The predictor has already made a prediction about what you will do. If the predictor predicted you would take only box B, it put $1 million in box B. If the predictor predicted you would take both boxes, it put nothing in box B. The predictor has a near-perfect track record. It's been right 99% of the time in previous trials. You have two choices: take only box B or take both box A and box B. What do you do? If you take only box B, the predictor almost certainly predicted this, and box B contains $1 million. You walk away with $1 million. If you take both boxes, the predictor almost certainly predicted this, and box B is empty. You walk away with just the $1,000 from box A. Taking only box B seems clearly better, and yet the predictor has already made its prediction. The money is already in the box, or it isn't. Nothing you do now can change what's in the box. Whatever is in box B is already there, so you should take both boxes because you get whatever is in box B plus an extra $1,000 from box A. Taking both boxes dominates, taking one box in every possible scenario. Both arguments are compelling, both are logically sound, and they give opposite answers. This is Newcomb's paradox, published in 1969 by the philosopher Robert Nozick, based on a problem posed by the physicist William Newcomb. It has divided decision theorists ever since. One camp, the one-boxers, argues that you should take only box B, because the predictor's track record shows that one-boxers walk away rich and two-boxers walk away poor. Another camp, the two-boxers, argues that the money is already in the box and dominance reasoning. Take the option that's better in every possible state of the world, should override any correlation with past predictions. Professional philosophers and mathematicians split roughly evenly between one-boxing and two-boxing, and the split doesn't correlate with expertise. Brilliant people land on both sides. The paradox also connects to the ancient debate about free will. If the predictor can predict your choice with near-perfect accuracy, in what sense are you free to choose? You might feel free. You might deliberate. But the predictor already knows what you'll decide. If your decision is predictable, is it really a choice? Some philosophers use Newcomb's paradox to argue that free will is compatible with determinism, that being predictable doesn't make you unfree. Others use it to argue the opposite, that the scenario is troubling precisely because it seems to strip you of genuine agency. Unlike the Monty problem, where one answer is correct and the other is wrong, Newcomb's paradox may not have a single right answer. It may be a case where two legitimate principles of rationality, expected utility maximization and dominance reasoning, genuinely conflict, and the paradox consists precisely in that conflict. The paradox cuts to the heart of what it means to make a rational decision. Expected utility theory, the dominant framework in economics and decision theory, says you should take one box because the expected utility of one boxing is much higher. Dominance reasoning, the principle that you should never choose an option that is worse in every possible state of the world, says you should take both boxes. These two principles are both considered fundamental to rational choice, and in Newcomb's paradox, they give opposite recommendations. Some philosophers have tried to dissolve the paradox by arguing that the scenario is impossible, that a perfect predictor can't exist, or that its existence would violate free will, but the paradox doesn't require a perfect predictor. A 90% accurate predictor creates essentially a similar dilemma, and predictors that are significantly better than chance at forecasting human behavior do exist. Behavioral algorithms used by tech companies predict user actions with high accuracy every day. Others have argued that the paradox reveals two legitimate types of rational decision-making that are normally aligned but diverge in unusual cases. Causal decision theory, which focuses on the causal consequences of your action, recommends two-boxing. Evidential decision theory, which focuses on what your action would tell you about the state of the world, recommends one-boxing. The debate between these two frameworks has generated a vast literature and remains one of the central disputes in decision theory. The philosopher Robert Nozick, who introduced the paradox, said he had changed his mind about it multiple times. To almost everyone, he wrote, it is perfectly clear and obvious what should be done. The difficulty is that these people seem to divide almost evenly on the problem, with large numbers thinking that the opposing half is just being silly. If you have a strong opinion about whether to take one box or two, hold it loosely. Very smart people hold the opposite opinion with equal conviction. The philosopher David Lewis was a committed two-boxer. The philosopher Robert Nozick leaned toward one boxing that was never fully settled. Surveys of professional philosophers show an almost perfect 50-50 split, year after year, decade after decade. The paradox doesn't resolve. It seems to be genuinely, permanently undecidable, not because of ignorance, but because two legitimate principles of rationality point in opposite directions and there is no higher principle that adjudicates between them. We're in the final stretch now. Two more paradoxes, each quieter and stranger than the ones that came before, and then the mathematics settles, and the paradoxes go to sleep. A researcher is studying a coin flip. Depending on the outcome, a subject, you, will be put to sleep and woken up either once or twice, with your memory of any previous awakening erased. Here is the protocol, and it's worth following carefully because the devil is in the details. A fair coin is flipped on Sunday. If it lands heads, you are woken up on Monday only. If it lands tails, you are woken up on Monday and again on Tuesday, with your memory of Monday's awakening erased before Tuesday. Each time you wake up, you don't know what day it is. Your experience upon awakening is identical regardless of whether it's Monday or Tuesday, and regardless of whether the coin landed heads or tails. You have no way to distinguish the awakenings. You're asked, what is your confidence that the coin landed heads? Before the experiment, you know the coin is fair, 50-50. You go to sleep. You wake up. The question is, has anything changed? The third opposition says 1/3. There are three possible awakening events: Monday heads, Monday tails, and Tuesday tails. You can't distinguish between them. Each is equally likely from your perspective. One of the three corresponds to heads, so your confidence should be 1/3. The half opposition says 1/2, reasoning as follows: the coin is fair. So you're confident, but quite white. You knew it was fair before you went to sleep. Being woken up gives you no new information about the coin, because you would be woken up regardless of the outcome. You're woken up on Monday whether the coin landed heads or tails. The halfer argues that since no new evidence has arrived, your probability should remain at its prior value. Updating without evidence would violate the basic rules of Bayesian reasoning. The thirder responds, but you should have expected to wake up twice as often in the tails world as in the heads world. From your perspective inside the experiment, you're more likely to be in a tails awakening than a heads awakening, because there are twice as many tails awakenings. Your perspective has changed, even if you haven't received any new external information. The change isn't in what you observe, but in what you are, an observer whose existence is correlated with the outcome. Your confidence that a fair coin landed heads should remain 1/2. This is the Sleeping Beauty problem, and like Newcomb's paradox, it splits experts roughly down the middle. Philosophers, mathematicians, and probability theorists have published hundreds of papers on it. There is no consensus. The problem touches on deep questions about the nature of probability, the role of evidence, and what it means to update your beliefs in situations where your own existence is observation dependent. The paradox is gentle. Nothing explodes, nobody loses money, nobody gets hanged, but the disagreement it generates is as fierce as anything in philosophy. The stakes are higher than they might seem. The Sleeping Beauty problem is structurally similar to questions that arise in cosmology. If the universe contains multiple copies of you, as some interpretations of quantum mechanics and some cosmological models suggest, how should you reason about probabilities? If you might be one of many observers, does the number of observers affect the probability you should assign to hypotheses about the world? These are questions about self-locating belief, about how to assign probabilities when you don't know which observer you are, and the Sleeping Beauty problem is their simplest and most precise formulation. Cosmologists call this the anthropic reasoning problem, and it's directly relevant to questions about the fine-tuning of physical constants, the probability of life in the universe, and the interpretation of quantum mechanics. The connection works like this. If the universe might contain many copies of you, whether through quantum branching, through the existence of multiple universes, or through the sheer size of an infinite cosmos, then learning that you exist is like waking up in the Sleeping Beauty experiment. You don't know which awakening you are. The number of possible awakenings depends on the hypothesis, and the question of whether the number of awakenings should affect your probabilities is exactly the question the thirders and halfers disagree about. If the thirders are right, the mere fact that you exist can shift the probability of cosmological hypotheses. If the halfers are right, your existence is evidentially inert. It tells you nothing about the universe beyond what you already knew. The stakes couldn't be higher. A toy problem about a sleeping woman and a coin flip turns out to be a stand-in for some of the deepest questions in philosophy of science, and the resolution, if there is one, may require rethinking what probability means at a fundamental level. And finally, a paradox from physics, not a thought experiment, not a mathematical curiosity, a genuine feature of the universe that nobody has fully explained. Every fundamental law of physics works equally well forward and backward in time. This is called time reversal symmetry, and it's one of the most counterintuitive facts in all of physics. Drop a ball. It falls, hits the ground, bounces, and eventually comes to rest. Film this and play it backward. A ball sitting on the ground spontaneously leaps into the air, gaining energy from nowhere. That looks absurd. That never happens. And yet, every individual interaction in the process, every collision between atoms, every transfer of energy is perfectly reversible. The laws governing each microscopic interaction don't care which direction time runs. But the macroscopic behavior, the ball falling versus leaping, emphatically does. The equations of Newton, Maxwell, Einstein, and Schrödinger don't distinguish between past and future. If you filmed a particle interaction and played the film backward, the reversed version would obey all the laws of physics just as well as the original. Time, in the equations, has no arrow, but the universe does. Ice melts, eggs break, people age, smoke disperses, heat flows from hot to cold. None of these processes happen in reverse spontaneously.